A cement is a binder, a substance that sets and hardens as the cement dries and also reacts with carbon dioxide in the air dependently, and can bind other materials together. The word cement traces to the Romans, who used the term opus caementicium to describe masonry resembling modern concrete that was made from crushed rock with burnt lime as binder. The volcanic ash and pulverized brick additives that were added to the burnt lime to obtain a hydraulic binder were later referred to as cementum, cimentum, current cement, and cement. Cements used in construction can be characterized as being either hydraulic or non-hydraulic, depending upon the ability of the cement to be used in the presence of water. Non-hydraulic cement will not set in wet conditions or underwater, and is attacked by some aggressive chemicals after setting. Hydraulic cement is made by replacing some of the cement in a concrete mix with activated aluminium silicates, pozzolaners, such as fly ash, to activate cement setting in wet condition or underwater and further protects hardened concrete from chemical attack. The chemical process for hydraulic cement found by ancient Romans used volcanic ash, to activate cement hardening between the anhydrous cement powder and water or plaster and water instead of relying on water drying out and simultaneously reacting with airborne carbon dioxide. Presently cheaper, pollution-free fly ash from power stations or other waste or byproducts are used as pozzolaners with plain cement to produce hydraulic cement. Pozzolaners can replace up to 40% of Portland cement. Thus, cement can harden underwater or when constantly exposed to wet weather. The chemical reaction results in hydrates that are not very water-soluble and so are quite durable in water and from chemical attack. Non-hydraulic cements and plasters do not harden in wet conditions. The most important uses of cement as an ingredient in the production of mortar in masonry, and of concrete, a combination of cement and an aggregate to form a strong building material. Chemistry. Non-hydraulic cement, such as slaked lime, harden by carbonation in presence of the carbon dioxide naturally present in the air. First, calcium oxide is produced by lime calcination at temperatures above 825 degrees Celsius for about 10 hours at atmospheric pressure, CaCO3 or Ca plus CO2. The calcium oxide is then spent mixing it to water to make slaked lime, Ca plus H2O or Ca, OH2. Once the water in excess from the slaked lime is completely evaporated, the carbonation starts, Ca, OH, 2 plus CO2 or CaCO3 plus H2O. This reaction takes a significant amount of time because the partial pressure of carbon dioxide in the air is small. The reaction of carbonation requires the air be in contact with the dry cement, hence, for this reason the slaked lime is a non-hydraulic cement and cannot be used underwater. This whole process is called the lime cycle. Conversely, the chemistry ruling the action of the hydraulic cement is hydration. Hydraulic cements are made of a mixture of silicates and oxides, the four main components being baelite, alite, cellate, brown millerite. The silicates are responsible of the mechanical properties of the cement. The cellate and the brown millerite are essential to allow the formation of the liquid phase during the cooking. The chemistry of the above-listed reactions is not completely clear and is still the object of research. History of the origin of cement. Cements before the 18th century, an early version of cement made with lime, sand, and gravel was used in Mesopotamia in the 3rd millennium BC and later in Egypt. It is uncertain where it was first discovered that a combination of hydrated non-hydraulic lime and a pozzolan produces a hydraulic mixture, but concrete made from such mixtures was first used by the ancient Macedonians and 3 centuries later on a large scale by Roman engineers. They used both natural pozzolans and artificial pozzolans in these concretes. Many excellent examples of structures made from these concretes are still standing, notably the huge dome of the Pantheon in Rome and the massive baths of Caracalla. The vast system of Roman aqueducts also made extensive use of hydraulic cement. Although any preservation of this knowledge in literary sources from the Middle Ages is unknown, medieval masons and some military engineers maintained an active tradition of using hydraulic cement in structures such as canals, fortresses, harbors, and shipbuilding facilities. This technical knowledge of making hydraulic cement was later formalized by French and British engineers in the 18th century. cements in the 18th, 19th, and 20th centuries, John Smeaton made an important contribution to the development of cement when he was planning the construction of the third Eddystone lighthouse in the English Channel now known as Smeaton's Tower. He needed a hydraulic mortar that would set and develop some strength in the 12-hour period between successive high tides. He performed experiments with combinations of different limestones and additives including tress and pozzolanas and did exhaustive market research on the available hydraulic limes, visiting their production sites, and noted that the hydraulicity of the lime was directly related to the clay content of the limestone from which it was made. Smeaton was a civil engineer by profession, and took the idea no further. In Britain particularly, good quality building stone became ever more expensive during a period of rapid growth, and it became a common practice to construct prestige buildings from the new industrial bricks, and to finish them with a stucco to imitate stone. Hydraulic limes were favored for this, but the need for a fast set time encouraged the development of new cements. Most famous was Parker's Roman cement. This was developed by James Parker in the 1780s, and finally patented in 1796. It was, in fact, nothing like material used by the Romans, but was a natural cement made by burning septaria nodules that are found in certain clay deposits, and that contain both clay minerals and calcium carbonate. The burnt nodules were ground to a fine powder. This product, made into a mortar with sand, set in 15 minutes. The success of Roman cement led other manufacturers to develop rival products by burning artificial hydraulic lime cements of clay and chalk. Roman cement quickly became popular but was largely replaced by Portland cement in the 1850s. In Russia, Igor Khelyev created a new binder by mixing lime and clay. His results were published in 1822 in his book A Treatise on the Art to Prepare a Good Mortar published in St. Petersburg. A few years later in 1825, he published another book, which described the various methods of making cement and concrete, as well as the benefits of cement in the construction of buildings and embankments. Apparently unaware of Smeaton's work, the same principle was identified by Frenchman Louis Vicat in the first decade of the 19th century. Vicat went on to devise a method of combining chalk and clay into an intimate mixture, and, burning this, produced an artificial cement in 1817 considered the principal forerunner of Portland cement, and Edgar Dobbs of Southwark patented a cement of this kind in 1811. James Frost, working in Britain, produced what he called British cement in a similar manner around the same time, but did not obtain a patent until 1822. In 1824, Joseph Aspdin patented a similar material, which he called Portland cement, because the render made from it was in colour similar to the prestigious Portland stone. However, Aspdin cement was nothing like modern Portland cement but was a first step in its development, called a proto-Portland cement. Joseph Aspdin's son William Aspdin had left his father's company and in his cement manufacturing apparently accidentally produced calcium silicates in the 1840s, a middle step in the development of Portland cement. William Aspdin's innovation was counterintuitive for manufacturers of artificial cements, because they required more lime in the mix, a much higher kiln temperature, and the resulting clinker was very hard and rapidly wore down the millstones, which were the only available grinding technology of the time. Manufacturing costs were therefore considerably higher, but the product set reasonably slowly and developed strength quickly, thus opening up a market for use in concrete. The use of concrete in construction grew rapidly from 1850 onward, and was soon the dominant use for cements. Thus Portland cement began its predominant role. Isaac Charles Johnson further refined the production of Meso-Portland cement and claimed to be the real father of Portland cement. Setting time and early strength are important characteristics of cements. Hydraulic limes, natural cements, and artificial cements all rely upon their bolite content for strength development. Bolite develops strength slowly. Because they were burned at temperatures below 1250 °C, they contain no oolite, which is responsible for early strength in modern cements. The first cement to consistently contain oolite was made by William Aspdin in the early 1840s, This was what we call today modern Portland cement. Because of the air of mystery with which William Aspdin surrounded his product, others have claimed precedence in this invention, but recent analysis of both his concrete and raw cement have shown that William Aspdin's product made at Northfleet, Kent was a truolite-based cement. However, Aspdin's methods were rule of thumb. Vicat is responsible for establishing the chemical basis of these cements, and Johnson established the importance of sintering the mix in the kiln. Sorel cement was patented in 1867 by Frenchman Stanislas Sorel and was stronger than Portland cement, but its poor water-resistive and corrosive qualities limited its use in building construction. The next development with the manufacture of Portland cement was the introduction of the rotary kiln, which allowed a stronger, more homogeneous mixture and a continuous manufacturing process. Also, tubby, a wall-building method using lime, sand and oyster shells to form a concrete, was introduced to the Americas by the Spanish in the 16th century. The lime may have been made from burned oyster shells, which were available in some coastal areas in the form of shell middens. Calcium aluminate cements were patented in 1908 in France by Jules Bide for better resistance to sulfates. In the U.S., the first large-scale use of cement was Rosendale cement, a natural cement mined from a massive deposit of a large dollarstone rock deposit discovered in the early 19th century near Rosendale, New York. Rosendale cement was extremely popular for the foundation of buildings and lining water pipes. But its long curing time of at least a month made it unpopular after World War I in the construction of highways and bridges, and many states and construction firms turned to the use of Portland cement. Because of the switch to Portland cement, by the end of the 1920s of the 15 Rosendale cement companies, only one had survived. But in the early 1930s it was discovered that, while Portland cement had a faster setting time, it was not as durable, especially for highways, to the point that some states stopped building highways and roads with cement. Bertrand H. Waite, an engineer whose company had worked on the construction of the New York City's Catskill Aqueduct, was impressed with the durability of Rosendale cement, and came up with a blend of both Rosendale and synthetic cements which had the good attributes of both. It was highly durable and had a much faster setting time. Mr. Waite convinced the New York Commissioner of Highways to construct an experimental section of highway near Newport, New York, using 1 sack of Rosendale to 6 sacks of synthetic cement. It was proved a success, and for decades the Rosendale synthetic cement blend became common use in highway and bridge construction. Modern cements. Modern hydraulic cements began to be developed from the start of the Industrial Revolution, driven by 3 main needs: hydraulic cement render for finishing brick buildings in wet climates, hydraulic mortars for masonry construction of harbor works, etc., in contact with seawater. Development of strong concretes. Types of modern cement. Portland cement. Portland cement is by far the most common type of cement in general use around the world. This cement is made by heating limestone with small quantities of other materials to 1450 degrees Celsius in a kiln, in a process known as calcination, whereby a molecule of carbon dioxide is liberated from the calcium carbonate to form calcium oxide, or quicklime, which is then blended with the other materials that have been included in the mix. The resulting hard substance, called clinker, is then ground with a small amount of gypsum into a powder to make ordinary Portland cement, the most commonly used type of cement. Portland cement is a basic ingredient of concrete, mortar and most non-specialty grout. The most common use for Portland cement is in the production of concrete. Concrete is a composite material consisting of aggregate, cement, and water. As a construction material, concrete can be cast in almost any shape desired, and once hardened, can become a structural element. Portland cement may be gray or white. Energetically modified cement. The grinding process to produce energetically modified cement yields materials made from pozzolanic minerals that have been treated using a patented milling process. This yields a high-level replacement of Portland cement in concrete with lower costs, performance and durability improvements, with significant energy and carbon dioxide savings. The resultant concretes can have the same, if not improved, Physical characteristics is normal concretes, at a fraction of the cost of using Portland cement. Portland cement blends. Portland cement blends are often available as interground mixtures from cement producers, but similar formulations are often also mixed from the ground components at the concrete mixing plant. Portland blast furnace cement contains up to 70% ground granulated blast furnace slag, with the rest Portland clinker and a little gypsum. All compositions produce high ultimate strength, but as slag content is increased, early strength is reduced, while sulfate resistance increases and heat evolution diminishes. Used as an economic alternative to Portland sulfate-resisting and low-heat cements. Portland fly ash cement contains up to 35% fly ash. The fly ash is pozzolanic, so that ultimate strength is maintained. Because fly ash addition allows a lower concrete water content, early strength can also be maintained. Where good quality cheap fly ash is available, this can be an economic alternative to ordinary Portland cement. Portland pozzolan cement includes fly ash cement, since fly ash is a pozzolan, but also includes cements made from other natural or artificial pozzolans. In countries where volcanic ashes are available, these cements are often the most common form in use. Portland silica fume cement. Addition of silica fume can yield exceptionally high strengths, and cements containing 5–20% silica fume are occasionally produced. However, silica fume is more usually added to Portland cement at the concrete mixer. Masonry cements are used for preparing bricklaying mortars and stuccos, and must not be used in concrete. They are usually complex proprietary formulations containing Portland clinker and a number of other ingredients that may include limestone, hydrated lime, air entrainers, retarders, waterproofers and coloring agents. They are formulated to yield workable mortars that allow rapid and consistent masonry work. Subtle variations of masonry cement in the U.S. are plastic cements and stucco cements. These are designed to produce control bond with masonry blocks. Expansive cements contain, in addition to Portland clinker, expansive clinkers, and are designed to offset the effects of drying shrinkage that is normally encountered with hydraulic cements. This allows large floor slabs to be prepared without contraction joints. White blended cements may be made using white clinker and white supplementary materials such as high-purity metakaolin. Colored cements are used for decorative purposes. In some standards, the addition of pigments to produce colored Portland cement is allowed. In other standards, pigments are not allowed. Constituents of Portland cement, and colored cements are sold as blended hydraulic cements. Very finely ground cements are made from mixtures of cement with sand or with slag or other pozzolan-type minerals that are extremely finely ground together. Such cements can have the same physical characteristics as normal cement but with 50% less cement, particularly due to their increased surface area for the chemical reaction. Even with intensive grinding, they can use up to 50% less energy to fabricate than ordinary Portland cements. Pozzolan lime cements. Mixtures of ground pozzolan and lime are the cements used by the Romans, and can be found in Roman structures still standing. They develop strength slowly, but their ultimate strength can be very high. The hydration products that produce strength are essentially the same as those produced by Portland cement. Slag lime cements. Ground granulated blast furnace slag is not hydraulic on its own, but is activated by addition of alkalis, most economically using lime. They are similar to pozzolan lime cements in their properties. Only granulated slag is effective as a cement component. Supersulfated cements contain about 80% ground granulated blast furnace slag, 15% gypsum or anhydrite and a little Portland clinker or lime as an activator. They produce strength by formation of ettringite, with strength growth similar to a slow Portland cement. They exhibit good resistance to aggressive agents, including sulfate. Calcium aluminate cements are hydraulic cements made primarily from limestone and bauxite. The active ingredients are monocalcium aluminate Ca-Al2O4 and meionite Ca12Al14033. Strength forms by hydration to calcium aluminate hydrates. They are well adapted for use in refractory concretes, for example for furnace linings. calcium sulfoaluminate cements are made from clinkers that include euelemite 6SO4 or C4A3S in cement chemists' notation, as a primary phase. They are used in expansive cements, in ultra-high early-strength cements, and in low-energy cements. Hydration produces ettringite, and specialized physical properties are obtained by adjustment of the availability of calcium and sulfate ions. Their use as a low-energy alternative to Portland cement has been pioneered in China, where several million tons per year are produced. Energy requirements are lower because of the lower kiln temperatures required for reaction, and the lower amount of limestone in the mix. In addition, the lower limestone content and lower fuel consumption leads to a CO2 emission around half that associated with Portland clinker. However, SO2 emissions are usually significantly higher. Natural cements correspond to certain cements of the pre-Portland era, produced by burning argillaceous limestones at moderate temperatures. The level of clay components in the limestone is such that large amounts of bolite are formed without the formation of excessive amounts of free lime. As with any natural material, such cements have highly variable properties. Geopolymer cements are made from mixtures of water-soluble alkali metal silicates and aluminosilicate mineral powders such as fly ash and metakaolin. Curing, cement sets or cures when mixed with water, which causes a series of hydration chemical reactions. The constituents slowly hydrate and crystallize. The interlocking of the crystals gives cement its strength. Maintaining a high moisture content in cement during curing increases both the speed of curing and its final strength. Gypsum is often added to Portland cement to prevent early hardening or flash setting, allowing a longer working time. The time it takes for cement to cure varies depending on the mixture and environmental conditions. Initial hardening can occur in as little as 20 minutes, while full cure can take over a month. Cement typically cures to the extent that it can be put into service within 24 hours to a week. Safety issues. Bags of cement routinely have health and safety warnings printed on them because not only is cement highly alkaline, but the setting process is exothermic. As a result, wet cement is strongly caustic and can easily cause severe skin burns if not promptly washed off with water. Similarly, dry cement powder in contact with mucous membranes can cause severe eye or respiratory irritation. Some ingredients can be specifically allergenic and may cause allergic dermatitis. Reducing agents are sometimes added to cement to prevent the formation of carcinogenic chromate in cement. Cement users should wear protective clothing. Cement industry in the world. In 2010, the world production of hydraulic cement was 3,300 million tons. The top three producers were China with 1,800, India with 220, and USA with 63.5 million tons, for a combined total of over half the world total by the world's three most populated states. For the world capacity to produce cement in 2010, the situation was similar, with the top three states accounting for just under half the world total capacity. Over 2011 and 2012, global consumption continued to climb, rising to 3585 mt in 2011 and 3736 mt in 2012. While annual growth rates eased to 8.3% and 4.2%, respectively. China, representing an increasing share of world cement consumption, continued to be the main engine of global growth. By 2012, Chinese demand was recorded at 2160 mt, representing 58% of world consumption. Annual growth rates, which reached 16% in 2010, appear to have softened, slowing to 5.6% over 2011 and 2012, as China Euro unregistered trademark S economy targets a more sustainable growth rate. Outside of China, worldwide consumption climbed by 4.4% to 1462 mt in 2010, 5% to 1535 mt in 2011, and finally 2.7% to 1576 mt in 2012. Iran is now the third largest cement producer in the world and has increased its output by over 10% from 2008 to 2011. Due to climbing energy costs in Pakistan and other major cement-producing countries, Iran is a unique position as a trading partner. utilizing its own surplus petroleum to power clinker plants. Now a top producer in the Middle East, Iran is further increasing its dominant position in local markets and abroad. The performance in North America and Europe over the 2010-12 period contrasted strikingly with that of China, as the global financial crisis evolved into a sovereign debt crisis for many economies in this region and recession. Cement consumption levels for this region fell by 1.9% in 2010 to 445 mt, recovered by 4.9% in 2011, then dipped again by 1.1% in 2012. The performance in the rest of the world, which includes many emerging economies in Asia, Africa and Latin America and representing some 10-20 mt cement demand in 2010, was positive and more than offset the declines in North America and Europe. Annual consumption growth was recorded at 7.4% in 2010, moderating to 5.1% and 4.3% in 2011 and 2012, respectively. As at year-end 2012, the global cement industry consisted of 5673 cement production facilities, including both integrated and grinding, of which 3,900 were located in China and 1,773 in the rest of the world. Total cement capacity worldwide was recorded at 5245 mt in 2012, with 2950 mt located in China and 2295 mt in the rest of the world. China. For the past 18 years, China consistently has produced more cement than any other country in the world. China's cement export peaked in 1994 with 11 million tons shipped out and has been in steady decline ever since. Only 5.18 million tons were exported out of China in 2002. Offered at $34 a ton, Chinese cement is pricing itself out of the market as Thailand is asking as little as $20 for the same quality. In 2006, it was estimated that China manufactured 1.235 billion tons of cement, which was 44% of the world total cement production. Demand for cement in China is expected to advance 5.4% annually and exceed 1 billion tons in 2008, driven by slowing but healthy growth in construction expenditures. Cement consumed in China will amount to 44% of global demand, and China will remain the world's largest national consumer of cement by a large margin. In 2010, 3.3 billion tons of cement was consumed globally. Of this, China accounted for 1.8 billion tons. Africa. Environmental impacts. Cement manufacture causes environmental impacts at all stages of the process. These include emissions of airborne pollution in the form of dust, gases, noise and vibration when operating machinery and during blasting in quarries, and damage to countryside from quarrying. Equipment to reduce dust emissions during quarrying and manufacture of cement is widely used, and equipment to trap and separate exhaust gases are coming into increased use. Environmental protection also includes the reintegration of quarries into the countryside after they have been closed down by returning them to nature or recultivating them. CO2 emissions. Carbon concentration in cement spans from a per mil 5% in cement structures to a per mil 8% in the case of roads and cement. Cement manufacturing releases CO2 in the atmosphere both directly when calcium carbonate is heated, producing lime and carbon dioxide, and also indirectly through the use of energy if its production involves the emission of CO2. The cement industry produces about 5% of global man-made CO2 emissions, of which 50% is from the chemical process, and 40% from burning fuel. The amount of CO2 emitted by the cement industry is nearly 900 kg of CO2 for every 1,000 kg of cement produced. In the European Union, the specific energy consumption for the production of cement clinker has been reduced by approximately 30% since the 1970s. This reduction in primary energy requirements is equivalent to approximately 11 million tons of coal per year with corresponding benefits in reduction of CO2 emissions. This accounts for approximately 5% of anthropogenic CO2. The high proportion of carbon dioxide produced in the chemical reaction leads to a large decrease in mass in the conversion from limestone to cement. So, to reduce the transport of heavier raw materials and to minimize the associated costs, It is more economical for cement plants to be closer to the limestone quarries rather than to the consumer centers. In certain applications, lime mortar reabsorbs the same amount of CO2 as was released in its manufacture, and has a lower energy requirement in production than mainstream cement. Newly developed cement types from Novacem and EcoCement can absorb carbon dioxide from ambient air during hardening. Use of the Kalina cycle during production can also increase energy efficiency. Heavy metal emissions in the air, in some circumstances, mainly depending on the origin and the composition of the raw materials used, the high-temperature calcination process of limestone and clay minerals can release in the atmosphere gases and dust rich in volatile heavy metals. AO, thallium, cadmium and mercury are the most toxic. Heavy metals are often found as trace elements in common metal sulfides, zinc blende, galena. Present as secondary minerals in most of the raw materials. Environmental regulations exist in many countries to limit these emissions. As of 2011 in the United States, cement kilns are legally allowed to pump more toxins into the air than hazardous waste incinerators. Heavy metals present in the clinker. The presence of heavy metals in the clinker arises both from the natural raw materials and from the use of recycled byproducts or alternative fuels. The high pH prevailing in the cement porter limits the mobility of many heavy metals by decreasing their solubility and increasing their sorption onto the cement mineral phases. Nickel, zinc and lead are commonly found in cement in non-negligible concentrations. Use of alternative fuels and byproducts materials. A cement plant consumes 3 to 6 gigajoules of fuel per ton of clinker produced, depending on the raw materials and the process used. Most cement kilns today use coal and petroleum coke as primary fuels, and to a lesser extent natural gas and fuel oil. Selected waste and byproducts with recoverable calorific value can be used as fuels in a cement kiln, replacing a portion of conventional fossil fuels, like coal, if they meet strict specifications. Selected waste and byproducts containing useful minerals such as calcium, silica, alumina, and iron can be used as raw materials in the kiln, replacing raw materials such as clay, shale, and limestone. Because some materials have both useful mineral content and recoverable calorific value, the distinction between alternative fuels and raw materials is not always clear. For example, sewage sludge has a low but significant calorific value, and burns to give ash containing minerals useful in the clinker matrix. Normal operation of cement kilns provides combustion conditions which are more than adequate for the destruction of even the most difficult to destroy organic substances. This is primarily due to the very high temperatures of the kiln gases. The gas residence time at high temperature in the rotary kiln is of the order of 5–10 seconds and in the pre-calcine more than 3 seconds. Due to bovine spongiform encephalopathy in the European beef industry, the use of animal-derived products to feed cattle is now severely restricted. Large quantities of waste animal meat and bone meal, also known as animal flour, have to be safely disposed of or transformed. The production of cement kilns, together with the incineration, is to date one of the two main ways to treat this solid effluent of the food industry. Green cement. Green cement is a cementitious material and meets or exceeds the functional performance capabilities of ordinary Portland cement by incorporating and optimizing recycled materials, thereby reducing consumption of natural raw materials, water, and energy, resulting in a more sustainable construction material. The manufacturing process for green cement succeeds in reducing, and even eliminating, the production and release of damaging pollutants and greenhouse gases, particularly CO2. Growing environmental concerns and increasing cost of fuels of fossil origin have resulted in many countries in sharp reduction of the resources needed to produce cement and effluents. Peter Trimble, a design student at the University of Edinburgh, has proposed dupe based on Sporosarcina pastua, a bacterium with binding qualities which, when mixed with sand and urine, produces a concrete said to be 70% as strong as conventional materials. The idea has been commercialized in the USA. See also, BET theory, cement chemist notation, cement render, energetically modified cement, fly ash, geopolymers, Portland cement, Rosendale cement, Diosem, Ultratech cement. References Further reading, Additives, Pierre Claude. Cements of Yesterday and Today, Concrete of Tomorrow. Cement and Concrete Research 30, 1349 Euro 1359. doi, 10.1016 per second 0008-8846, 00-00365-3 Vanos, Hendrik G. Padovani, Amy C. Cement Manufacture and the Environment, Part 1, Chemistry and Technology. Journal of Industrial Ecology 6, 89 Euro 105 doi, 10.1162/10881980232097165 Vanos, Hendrik G. Padovani, Amy C. Cement Manufacture and the Environment, Part 2, Environmental Challenges and Opportunities. Journal of Industrial Ecology 7, 93 Euro 126 doi, 10.1162/1088198037667292212 Friedrich W. Locker, Cemental Principles of Production and Use, Dar 1 Quartersdorf, Germany, Verlag Bau plus Technik GmbH, 2006, ISBN 3-7640-0420-7, Jave Dibati, F. McGregor Miller, Stephen H. Kuzmitka. Editors, Innovations in Portland Cement Manufacturing, SP 400, Portland Cement Association, Skokie, Illinois, USA, 2004, ISBN 0-89312-234-3, Cement Industry is at Center of Climate Change Debate article by Elizabeth Rosenthal in the New York Times October 26, 2007, Neville, A.M. Properties of Concrete. Fourth and Final Edition Standards. Pearson, Prentice Hall. ISBN A0-582-23070-5. OCLCA 33837400 Taylor, H.F.W. Cement Chemistry. Academic Press. PA 475. ISBN A0-12-683900 Ulm, Franz Joseph. Roland J.M. Pelnk, Akira Koshima, Roots B. Shah Savari, Christine J. Van Vliet, Marcus J. Wheeler, Sidney Yip. A Realistic Molecular Model of Cement Hydrates. Proceedings of the National Academy of Sciences 106, 16102 Euro 16107. doi, 10.1073/FNAS 0902180106 External links